good afternoon, Grade 12s. I hope that you're all doing well. I miss you all terribly. I hope that you guys are surviving without our regular physical sciences class. I thought I'd make some videos for us just to get started on a new term of work. Today we'll be looking at Module 1, Unit 3, which is work, energy and power. So let's get into it. Alright, welcome to our first lesson. So what we're going to be looking at today is Module 1, Unit 3, the work, energy and power. Now this picks up after Module 1, Unit 2, of course, which was vertical projectile motion. It's the first unit of Term 2 that we'll be working on. So before I go any further, if we have a look there at the second word, the word energy, that's something that actually all three of these words we've seen before, but energy is quite a difficult concept for us to put down simply. However, we do have a handy definition, and this should inform the rest of our module because it shows us how all of these are integrally linked: work, energy and power. All of these are related to each other. So we have a look here, definition for energy. Very simply, it's going to be the ability to do work. So clearly we need to have a look at work. Now, in order to do that, we're going to turn to our exam guidelines. You should have your copies with you. If you don't, I will display it on the screen. I'll also put a link up so that you can access the rest of the PDF during your time at home. So if we have a look there at work, we define the work done on an object by a constant force F as F delta X cos theta, where F is the magnitude of the force, delta X the magnitude of the displacement, and theta the angle between the force and the displacement. Now, what we're actually doing there, in order to define our work, all we need to remember, of course, is the equation. Work is equal to F multiplied with delta X multiplied with cos theta. Now, that cos theta is important. We can actually take the F and the cos theta out of there, because if we consider a force, let's say it's acting diagonally, let's say that is my force, then I'm going to have, if I look at on the horizontal, then if I bring my force down to the horizontal, that magnitude there, or that length over there, if this is theta, then that is going to be F times cos theta. So what we see is we've actually taken the F down into the horizontal, or down onto into any direction, really. All right. Now, if we put our displacement on that same line, then we can see that what I'm actually doing, in order to calculate my work, I'm multiplying the component of force that is parallel to my displacement with my displacement. So I'm taking that F cos theta and multiplying it with my delta X, my displacement. Now we can see that they're both that both of them are pointing in the same direction. Now, this cos theta the fact that we're using cos theta here gives rise to a lot, kind of simplifies things for us a lot. For instance, if I have, let's say, a situation where I have my displacement towards the right and then my force vertically upwards, we can see that there is a 90-degree angle between them. Now, the angle between the force and displacement, remember that's my theta, so here my theta is equal to 90 degrees. And if we remember our cos graphs and just our trigonometry in general, we should know that cos 90 degrees is always going to be 0. So if I were to calculate the work done by this force on my object while the object is moving towards the right with a certain displacement, I can immediately see that, well, this force is going to do 0 work on my object because the two are perpendicular to each other. Now let's see if we have a look at some examples, if this becomes a bit clearer, we're going to start it off simple. Example 1, where we're just going to put an object on a surface. So we've got our surface over there, and we've got our object, usually a block like we draw. And we're going to say, for instance, that this object is moving from this point to that point. So we draw in our displacement. Let's say that's my delta x. Let's say, for argument's sake, my delta x is 3 meters. So that means the block is being moved 3 meters towards the right. And if while the block is moving 3 meters towards the right, a force is being applied on that block. Let's say it's being pushed or pulled, it doesn't really matter. And there is a force of 10 newtons. Now I want to calculate what work, or what's the amount of work that force of 10 newtons does on this object while it's moving 3 meters. It's very simple. I just use my equation. I say work is equal to F times delta x times cos theta. I substitute in the values. The force is going to be 10 newtons. Displacement is going to be 3 meters. And my cos, I'm going to put in an angle there. Now, what on earth could that angle be? Well, we see that force is towards the right and displacement is towards the right. So they are parallel to each other. That would mean that my angle is 0 degrees. Perhaps that's a bit unclear, so if we draw a free body diagram, I can show here that my force is towards the right and my displacement is towards the right. These two would lie on top of each other, so clearly my angle is 0 degrees. Alright, so cos of 0 degrees, we know that that's equal to 1. If we just look at that guy over there, cos of 0 degrees is always going to be equal to 1. So in fact here, when my force is acting parallel to my displacement, then my work is at what we call a maximum. As the angle changes, my work is going to change, even though my force and my displacement remains the same. So we can see here that my work is just going to be, well, that's obviously not going to have a unit, so I'm going to have 10 newtons times 3 meters. That gives me 30 Newton meters, and that is the same as saying 30 joules. We'll have a look perhaps at that later, at that derivation. Not too important, but very important here is that we remember we're working with work, so my unit for work is going to be joules, the same as for energy. Let's have a look at our next example. So we say example 2, and here what we're going to do is we're going to have a similar situation. So again, I've got a box lying on a surface. It's again moving from that point to that point. So my displacement is going to, let's say again 3 meters, it's moving 3 meters, but now my force is acting at an angle. We say it's still 10 newtons, however we shall say that this is 30 degrees. So my force is acting at a 30 degree angle above the horizontal. So to calculate the work here, we say again, work is equal to F times delta x times cos theta. Nothing strange there. So I say that's going to be 10 times 3 times cos, and now the angle is going to be 30 degrees. Perhaps if we draw a free body diagram, that becomes a bit clearer. Let's draw it underneath here. So I'm just going to move up a bit. We have our displacement over there, and then 30 degrees above the horizontal, above the displacement, I have my net force. So that's my F. So I've got my 30 degrees over there. So we can clearly see that because my displacement is horizontal, my force is 30 degrees above the horizontal, there's going to be a 30 degree angle between the two. So I punch that into my calculator. I say 10 times 3 times cos of 30, and that gives me an answer of 25,98 joules. 25,98 joules. Alright. Now, this has all been quite simple and straightforward. However, they're not always going to be, my force and my displacement aren't always going to be in the same direction. So if we have a look at our next example, we'll see what I'm talking about. Let's say again we've got a surface. We've got our lovely box on our surface, and it's again moving from that point to that point. We say again it's just moving 3 meters, so delta x is equal to 3 meters. And then the force is no longer, it's still going to be 10 newtons because we're going to keep it simple, but it's not pulling it towards that side, it's pulling it towards the left. So we say F equals 10 newtons. Now you might be asking yourself, how is this possible? How can the box be moving towards the right from point A to point B with a displacement of 3 meters towards the right? However, the force is in the opposite direction. Well, we know that this would be a scenario where the object is moving towards the right originally, but it's going to start slowing down because the force here is applied in the opposite direction. We don't see any other forces really, so this should be our net force. There will be, of course, our force of gravity and our normal force, but those are going to be cancelling out. They're not going to change my net force. So this scenario, even though they're in the opposite direction, is perfectly possible. It's just going to mean in the real world this object is going to be slowing down. So let's see if we can calculate my work done by that 10 newtons on the box moving towards the right. So we say work again is equal to F delta x cos theta, and that's going to give me again 10 newtons multiplied with 3 multiplied with cos, and now the angle here is again, how do we know what that angle is? Well, the angle is going to be 180 degrees. We can say a word here that we can say that the force and the displacement are actually anti-parallel. So they're along the same line. They're still both horizontal, but the one's horizontally towards the left, the other one to the right. Again, free body diagram makes this pretty clear. We've got my delta x towards the right, my f towards the left, and we can see there's my 180 degrees in my straight line. Okay, so cos 180, we should know that that is going to give me a minus 1. So what do I mean by that? Well, if I just focus on my cos 180 degrees, we say cos 180 degrees is always going to give me a minus 1. All right, should know this. This is one of the points that you should know on your cos graph, for instance, to make it a little bit easier in mathematics. But let's have a look here. So I can immediately see this is going to give me, let's type it into our calculator just to be sure. What do we say? 10 times 3 times cos of 180, and that gives me an answer of minus 30 joules. So I've got what we call negative work done on the object. What that means, if we look later on at our work energy theorem, is that this is actually going to be slowing down my object, or in other words, decreasing my kinetic energy. All right. Because work energy's theorem says the net work done on an object is going to be equal to the change in the object's kinetic energy. Alright, so we can see here what happens when the forces are in opposite directions. But let's see one more example here. We're going to look at example 4. And again, just have an object on a surface. Nice block like we always do. Again, moving from point A to point B, I'm going to say my displacement is still 3 meters towards the right, but now my force, its magnitude is the same, it's still going to be equal to 10 newtons. However, the angle is going to be 30 degrees above the horizontal on the left. Alright, so how do I calculate the work here? Same equation, work equals F times delta x cos theta. Force is 10 newtons, displacement is 3 meters. The angle here is going to be, again, what? Well, I'm sure you can, you know what's coming next. Well, let's draw a free body diagram quickly. We've got my displacement towards the right, and I've got a little dotted line there. Don't have to include that, but that's just so that we can see that my force is going to be that line over there. So we've got that 30 degrees over there. Now the dotted line and the displacement actually forms a straight line, so that's 180 degrees, but then I'm less 30, so I say 180 minus 30, and then this angle here between displacement and force is going to be 150 degrees. So I put my 150 degrees in there, I punch it in. Now if we, again, trigonometry, maths, all of those lovely things, if we have a look here, we can see I'm in the second quadrant, so cos is going to be negative. And that means I'm going to, I actually know what the answer is going to be here already. We can kind of cheat and have a look at our previous one. We've got 25,98, but it's going to be negative 25,98 joules. Just to confirm, we type it into our calculators, 10 times 3 times cos 150, and it gives me negative 25,98 joules. All right. So we're going to have a look at some classwork, but before we do that, I just want to remind everyone of our classroom website. That is Pretorius Lab 129.wordpress.com. I will post a link to some of the resources that the resources that we'll be using here, and we are going to be doing some classwork from the Siavula textbook, because I'm worried that some of us may have forgotten our textbook, although most of you should have your textbooks after the exams, but it's called the Siavula Physical Sciences grade 12, and I will include a link to that in the description or on the classroom website. So let's have a look at some classwork. We are going to be looking at exercise, I think it's exercise 5.1, and this is on page 237 of the PDF of the Siavula grade 12 textbook, and we are going to start off with number 1. I will also put that in the video now. Let's have a look at that quickly. So a 10 Newton force is applied to push a block across a frictionless surface for a displacement of 5 meters to the right. The block has a weight Fg of 20 newtons. Determine the work done by the following forces: the normal force, the weight Fg, and the applied force. Now, you can see that they've given us a force diagram there. However, I'm going to just draw a quick little free body diagram there. We've got my F applied there. They say that that's going to be equal to 10 newtons. Then we have my normal force there, Fn, and then I also have my Fg. Now my Fg, they tell us, is 20 newtons. Nothing here, there's no ropes being pulled up or down, so my normal force and my force of gravity, those are going to cancel out, so give me a net force of 0, so that's going to be 20 newtons for my normal force as well. And then my displacement, they say, is also going to be towards the right. So I'm just going to draw my delta x there. That's going to be 5 meters. Now, we can immediately see here that my Fn and my Fg, these are both perpendicular to my displacement. So, right off the bat, let's say my work of my Fn, that's going to be Fn times delta x times cos theta. Doesn't matter what my normal force, what my displacement is here, my theta is going to be 90 degrees. So I can immediately say that's going to be 0 newtons, because these two are, my normal force is perpendicular to my displacement. In the same way, the work done by Fg, it's also going to be, yes, Fg delta x cos theta, but that's also going to be 0 newtons, because it's also perpendicular. The angle between my displacement and my Fg is actually in this case going to be 270 degrees. But if we say cos of 270 degrees, that's also going to give me 0. Another point that we should know on our cos graph. Now, what about the work done by F applied? Well, there we've got F applied times delta x times cos theta, and here we can see that they are parallel to each other. They're pointing in the same direction, so my theta is equal to 0. So we just put everything in there. My applied force is 10 newtons. My displacement is going to be 5 meters, and I say cos of 0 degrees, that's going to give me give me 50 joules of work, and we can see that it's positive work that's done. All right, then we're going to jump right to the end of the example to do something a little bit, or exercise to do something a little bit more difficult. We're going to have a look at number 10. You should be able to see that on the screen now. And they tell us that a student with a mass of 60 kilograms runs up 3 flights of stairs in 15 seconds, covering a vertical distance of 10 meters. Determine the amount of work done by the student to elevate her body to this height. So let's draw a free body diagram here. Force downwards is Fg, and that's going to be equal to mg, isn't it? We've got a mass, and mass of 60 kilograms of the student, and we should know gravity is 9.8 meters per second squared. Then we have a force acting upward. That's going to be my F applied. Now, there aren't any other forces. We're assuming that this person is not moving up faster and faster and faster, so I've got a F net of 0, so F applied is actually going to be equal to the force of gravity in this case. And therefore the work that she does, we can just say work is equal to F applied times delta x times cos theta. Now she is moving upwards, so we should just include my delta x there. We can see that there's an angle of 0 between the two, so I write my F applied is going to be mass times gravity times delta x times cos theta. The mass of the student is 60 kilograms, gravitational acceleration is 9.8, and the displacement here is going to be a vertical distance of 10 meters, and then I say cos of 0 degrees should give me an answer of 5,880 joules. Now we could actually, it wasn't asked in the question, but we could similarly be asked what is the work done by the force of gravity. Well, we would just make that a negative 5,880 because the magnitude of the force of gravity is the same, of course, but it's at an angle of 180 degrees to my displacement. All right, so it's important to note here what an important role theta plays. If my angle is kind of towards the same direction as my displacement, I'm going to have positive work that's done. If it's in the opposite direction, it's going to be negative work that's done. But always, if my force is perpendicular to the displacement, my work is going to be 0. 0 work done by a perpendicular force. That can be whether it's at 90 degrees or at 270 degrees. All right, thank you. Have a look at the rest of that exercise. It's at 5.3. Sorry, 5.1. I told you which pages you can find it on. I will include a link to all of the Siavula textbook, so the textbook as well as the teacher's guide. Feel free to use the teacher's guide to do some additional questions. And then in your DBE papers, you can do your question 5. Question 5. You won't be able to do that yet, but that's going to be in your paper 1, question 5. That's going to be your question testing you on work, energy, and power. We're not quite there yet, but in the future you'll be able to start doing some of the past paper questions as well. All right, enjoy the rest of your day.